Hi everyone. So my project is using Lidar to inform wetland restoration in Yosemite Valley. I want to, one, classify the existing vegetation on the site, and two, create a bare earth DEM that I can then extract elevation data from to plan the uh, elevation of a proposed wetland restoration project. So my original idea was similar. I wanted to classify a flood inundation map of the entire Yosemite Valley, which I realized is too large in scale, and river elevational change really caused a lot of problems with hydrologic modeling that I'm not capable of dealing with. So I decided to focus more instead on a smaller area of one meadow and explore a theoretical wetland restoration project. This allowed me to manipulate data a lot quicker and uh, play around with getting it right. And it also essentially flattened out the river so I could do some simple hydrologic uh, flood models. So I'm proposing and exploring the restoration of a parking lot outlined in pink, which is adjacent to the Merced River in Yosemite Valley. We know that this area floods annually, but approximately 5 days out of the year, which is, if we're making a wetland project, we would like it to be flooded much more than that, approximately 90 days out of the year. So park management wants to know what the current elevation of the parking lot is. They want to know what the elevation would need to be for it to be inundated for 90 days out of the year. And then they want to know the difference between that and the volume of earth that's going to be needed to be removed for this wetland project. They're also interested in just what kind of vegetation type currently exists in the restoration site. I downloaded 2 publicly available datasets for band NAPE imagery from USGS Earth Explorer and a LiDAR point cloud from Open Topography. The point cloud came as classified as ground and unclassified, and for the project I moved everything back to unclassified. I knew I was going to have to do hydro flattening, so I knew I was going to be digitizing streams and center lines anyways. So I went ahead and did that first, and then used my digitized stream polygons to then move into LP360 and classify by feature the points within the streams. I used the profile tool to move incorrectly classified water points such as bridges and high overhanging trees back to unclassified for further classification. So I've already classified all of my data, but I declassified a small portion just to run the macro for demonstration. After I classified my water points, then I classified everything back to unclassified, where I'll pick it up from here. I generated seed points and created a ground points. I then classified vegetation by having multiple return combinations, and then classified vegetation by height, low, medium, and high, as well as classified used a high noise filter. And I also classified buildings. There are some in the larger Lidar data set, but being a national park, there's really not a lot, and in the project area specifically, there are none. And so there you have it, the bare ground, and then green, yellow, and pink is vegetation by height, and the river obviously is still there, and the project boundary right here. That was the bulk of the point classification, but then there was a couple bridges within the project area. So I went through and used manual classification via the profile tool and 3D window. So one of my favorite and more challenging but very important tasks in this project was hydroflattening. I think this is something I'm interested in and would use, and challenged me a little bit in the labs, so I was glad to use it here. So you're looking at basically a before and after here of the ground 10 by elevation, and my process was conflate the river polygons using a drape method, and then conflate the river center lines using the downstream constraint. So that turned the 2D into 3D shapefile. And then in the ArcMap, use the river flatten tool with those 3D shapes, and then break line enforcement. And this was one of the more time-consuming aspects of the project, just because I wanted to understand it, and it took me quite a few times to get it right. And seeing as how there's several steps in the process too, but in the end, you could see that it turned out flat. So that was the bulk of the LP360 data processing work. After I classified all the points and hydroflattened the river, then exported a ground point hydroflattened break line enforced 10. Okay, so once I had the 10, I ran the summary statistics tool in LP360 to find the max elevation in the restoration site of 1,210.11 meters. This represents the minimum elevation that would inundate the current project area completely. The river had an elevation of 1205 meters in elevation. This would represent the current elevation of the river. And we're looking for the project site to be inundated for 90 days out of the year. Currently, with its current elevation of 1210, it gets 5 days of inundation by the river. We hear from our hydrologist friends that to get 90 days inundation by the river, we would have to bring the height down to 1207.11. Okay, so here's the derivative product, the DEM, from the Lidar data that I created with the project site shown in pink. And so this is the original DEM with the current elevation of 1210 meters at the project site. And when the river reaches a level of 1207, this is what the inundation would look like at that elevation. You'd see that the project site is dry. So through clipping and raster calculator and a bunch of ArcGIS stuff, I managed to make a new DEM, which is exactly the same except for it changes the study site, reduces the elevation to the desired elevation of 1207. So the whole point of this project is moving the elevation of the project site down to 1207 meters from currently 1210 meters. So it would get inundated when the river reaches the level of 1207 meters. So this is what it would look like when the river reaches 1207 meters. And you see that in fact the study site is now inundated. So hopefully that would work, and with an anticipated river level of 1207 throughout the year of 90 days, then we would expect our project site to be inundated for about 90 days out of the year. So using raster calculator and the DEMs, I found the difference between the elevation at the current project site and the elevation of the proposed project site, and using the two raster DEMs took the difference and found using the surface volume 3D analyst tool, found the volume of that difference to be 50,495 cubic meters. So that represents the difference between the two. So that is the volume of earth that's going to need to be removed if you want to restore this parking lot to a wetland by lowering its max elevation in the boundary to be inundated from 1210 meters to 1207 meters. This is when President Obama visited Yosemite a couple of years ago, and this photo is taken basically right on the edge of the project I'm proposing. So I definitely got a lot of independent practice and use and experience in LP360, especially with hydroflattening and how to do that on my own and setting up break lines and stream center lines, etc. Also using the profile window and 3D window for manual classification on my own. I learned that a lot more, and really think the manual classification in the profile window is cool, how you can do above line, below line, and send filters of classes to a different class. Yeah, I learned a lot about that, and I like that a lot. Also, just generally running PCTs independently and selecting the appropriate ones and setting our own parameters and having to think about it as opposed to being told what to do was a good learning experience. I gained more experience working with and creating DEMs and exporting them, and just manipulating them and seeing the applications of them, which I used a lot in this project. The application of which gave me probably the hardest time using raster calculator and calculating on the polygon of my area of interest versus just two rasters that match up exactly. That was really frustrating. It was definitely a good suggestion to reduce my scope. It allowed me to kind of create a theoretical project, which I think was a really cool application of basically taking LiDAR data and turning it into a real product that you could then use for a restoration project. I think it was really cool to go through basically from the beginning to the end, and really enjoyed this project.